So this is what the master web interface looks like. The URL that I'm talking about, the Spark URL, you'll see is shown here, Spark master at Spark colon. That is the address identity of the container. And there's the port. So you want to copy this bit to use into the Spark worker. Remember that you can start this web interface. Easiest thing to do, start the notebook in the usual way, go into a terminal application, and that's mapped. You should just be able to do startmaster.sh. That should be a small s, by the way. Then if you have mapped port 8080, go to localhost 8080. You should see this interface. Now, one thing to note, because we are mapping from inside a container, these generated URLs here, so these are clickable. Of course, we're not running any workers, so nothing would happen there. And in any case, this is a screenshot. But if this were clickable, it will be looking for an address inside the container, not the correct one. So that's just something we can work around by using localhost and then the URL. That's just something to bear in mind. Once we've started the master, as I said, we can start the worker with that URL, as it says down here, startworker.show with that master URL. Here's the worker ID, and you can see some basic status. So when I said this is running in the container IP, you can see that, maybe you can't, that 127.2.1.17 is an address inside the container. So a bit tricky to map these. These is things we just map the ports when we go into the command. You can see in any case the number of cores that are being used here, which is 12, and the memory, which is 24 gigs. So actually quite a chunky application. Okay. And so the interesting part happens when we go into monitoring the executor. So this is running on localhost 4040, and you can see we get a number of tabs: the jobs, the stages, storage, environment, executors, and SQL. We'll explore these in the lab. You can see there are options here to show peak memory usage, peak execution time, various other items, things like how much data is being shuffled about, shuffle read, shuffle write. And depending on how you've constructed your cluster, these can take more or less time. So a shuffle is an expensive operation when running between multiple hosts on a network. Shuffling between cores is clearly going to be a lot faster. The thing you're really focused on is memory usage. And we'll be looking at that just in a second as to how you might do some optimizations here. So to do further investigation, you should be looking at minimizing partition sizes, how the data is divided, and shuffles. Remember that Spark has this delayed execution model where code isn't executed until there's a graph built, and then there are certain functions which cause that execution. So you can look at each point, you can add .explain to data frames, and they will show you the execution plan in detail for that particular Spark set of instructions. If you notice that explain shows, well, it will, shows that some pieces of computation are being executed multiple times. Remember, this isn't storing generic global variables. usually. It will generate the execution graph, and as you add more nodes to that execution graph, it will re-execute them. And this means it may execute several parts multiple times, and you may want to, if you notice that some particular stage in the execution is taking a long time, i.e. by that monitoring process we looked at a minute ago, then you can store intermediate data frames by annotating them with .cache. That causes them to stay in memory. Now you can get big wins with .cache. So if you find some key part of the computation fairly early on is being recalculated lots of times, you can cache that in memory. But you need to be quite careful, because as you store things in memory, it takes more and more memory, and there is a good possibility that actually you will run out of memory, which is obviously counterproductive. So you want to consider carefully what you're going to cache. For example, if you've got a data frame with lots of columns that you don't actually use, then don't store the whole thing in memory. Drop those columns or create a copy with a smaller number of columns and then store that in memory. And as with any optimization, don't spend a lot of time trying to work through making the computation more efficient when actually that step didn't take very long in the first case. So look at what you're actually doing using the monitoring programs, and then when you're trying to optimize later on, consider using .cache judiciously. You should also, by the way, cache is a quick fix, be looking at what you're executing and whether there are more efficient ways to actually do that computation. So hopefully those are some tips there to improve your program efficiency and certainly to monitor what's going on. It's worth mentioning, by the way, the commercial clusters, cloud-related clustering. This slide particularly talks about Amazon AWS Elastic MapReduce, which is a commercial implementation pre-configured for Spark. So you create clusters with that, with multiple machines. You can start those on the command line, as I've just heard, and once you've got that cluster, you can add jobs to that with Spark Submit, as we've been doing so far with our local work. You're going to find virtually identical application in Databricks running on Azure, so Microsoft Azure. You'll see there is a cluster option there. With the startup student account, you're actually limited to the number of CPUs you can have, but you should be able to have a cluster with a driver and a worker at least. So that's possible. And as a general point, of course, we're working with cloud, so you should be able to take input in your job from a bulk storage service like Azure Blob Service or S3 on